Hello, good afternoon to all of you. I hope all of you are doing well. So in today's class, we're going to discuss with the second set of instructions. So the first instruction that we're going to discuss is IN port address. So when IN instruction is executed, the content of the input port designated is read and the content is loaded into the accumulator. Again, I'll repeat it. Whenever IN instruction is executed, then the content of the designated port address is read and then it's loaded onto the accumulator. Now it requires 2 bytes, 3 machine cycles and 10 T states. Likewise, it has hex code as DV and flags. None of the flags are affected. Now, let us move on to the next instruction that is called as INRR. So, INR is an instruction that is capable of incrementing the content of the register by 1. Again, I'll repeat it. On execution, INR instruction increments the content of the register by 1 and the result is stored in the register. Now it requires 1 byte, 1 machine cycle and 4 T states. Again, I'll repeat it. It requires 1 byte, 1 machine cycle and 4 T states. Now the possible combination of INR with the associated registers are specified with the hex code for your perusal. Now flags. Sign flag, zero flag, parity, and auxiliary carry are affected by the result of the operation, whereas carry flag is not modified. Again, I'll repeat it. Sign flag, zero flag, parity flag, and auxiliary carry are affected by the result of the operation, whereas carry flag is not modified. Now, the next instruction that we're going to study is JNRM. Sorry, INRM. So, INRM instruction on execution is capable of incrementing the content of the memory location pointed to by HL pair by 1. Again, I'll repeat it. INRM instruction is capable of incrementing the content of the address location pointed to by HL pair by 1. Now it requires 1 byte, 3 machine cycles and 10 T states. Now the hex code is 34 and the flags, sign flag, zero flag, parity flag and auxiliary carry flag are affected by the result of the operation, whereas carry flag is not modified. Now likewise we have INX instruction. Now INX instruction is capable of so on execution, INR instruction increments the content of the register pair by 1. Again, I'll repeat it. On execution, INX instruction is capable of incrementing the content of the register by 1 and the result is stored in the register pair itself. Now, the instruction views the content of the register as 16-bit data or 16-bit number. Now, it requires 1 byte, 1 machine cycle and 60 states. Again, I'll repeat it. It requires 1 byte, 1 machine cycle and 60 states. Now, the possible combination of INX with the register pairs with the associated hex codes are there for your perusal. Now, flags. None of the flags are affected. Now let us move on to the next instruction that is called as JMP. Now JMP instruction it is called as unconditional jump. Okay, JMP instruction is also called as unconditional jump. So whenever JMP instruction is executed, the program execution is transferred to the memory location specified in the instruction. Again, I'll repeat it. Whenever JMP instruction is executed, the program execution is transferred to the address specified in the instruction. Now bytes, it requires 3 bytes, 3 machine cycles and 10 T states. Whereas hex code, it has associated hex code C3. Now flags, none of the flags are affected. And likewise, we have conditional jump instructions like the first one is JC. Now JC instruction on execution is capable of transferring the program execution to the memory location specified in the instruction if carry flag is set or carry flag is equals to 1. If carry flag is equals to 0, then no transfer takes place. Again, I'll repeat it. JC is on execution. It's capable of transferring program execution to the address specified in the instruction if carry flag is equals to 1 or carry flag is set. Right? If carry flag is equals to 0, then no transfer takes place. Now, bytes, machine cycle, and T states requirement. It requires 3 bytes, 2 machine cycles, and 7 T states in situation where the condition is not true, and it requires 3 bytes, 3 machine cycles, and 10 T states if the condition is true. And the associated hex code is DA. Now, the flags, none of the flags are affected. Now likewise, we'll move on to the next instruction that is called as JNC. Now JNC instruction on execution is capable of transferring the program execution to the memory address specified in the instruction if carry flag is equals to 0 or carry flag is not set. If carry flag is equals to 1, then no transfer takes place. Now it requires 3 bytes, 2 machine cycles and 70 states if the condition is false, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. And the associated hex code is D2. And flags, none of the flags are affected. Now likewise, JP is another instruction, jump on plus. So JP is an instruction that's capable of on execution transferring program execution to the address location specified in the instruction if sign flag is equals to 0. If sign flag is equals to 1, then no transfer takes place. Now it requires 3 bytes, 2 machine cycles and 70 states if the condition is not true, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. Now the hex code is F2 and flags, none of the flags are affected. Now JM. JM is another instruction that is capable of transferring program execution to the memory address specified in the instruction if sign flag is equals to 1. If sign flag is equals to 0, then no transfer takes place. Now the byte requirement, the machine cycle and T states are, it requires 3 bytes, 2 machine cycles and 7 T states if the condition is false, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. The associated hex code for JM instruction is FA, and none of the flags are affected. Now likewise, the next instruction that we have is JPE. Now JPE basically stands for jump on parity even. That is, when JPE instruction is executed, the program execution is transferred to the memory location specified in the instruction if parity is even or parity flag is equals to 1. If parity flag is equals to 0, then no transfer takes place. It requires 3 bytes, 2 machine cycles, 70 states if the condition is not true, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. Hex code is EA, and flags, none of the flags are affected. Now likewise we have JPO. Now jump on parity odd. The jump on parity odd instruction on execution transfers the program execution to the memory address specified in the instruction if the parity is odd or parity flag is equals to 0. If parity flag is equals to 1, then no transfer takes place. Now bytes, machine cycle and T states requirement. It requires 3 bytes, 2 machine cycles and 7 T states if the condition is not true, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. Now the associated hex code is E2, and none of the flags are affected. Now likewise we have JZ. Now JZ is an instruction that's capable of transferring program execution to the address specified if zero flag is equals to 1, jump on 0, right? So it transfers program execution to the address specified if 0 flag is equals to 1. If 0 flag is equals to 0, then no transfer takes place. It requires 3 bytes, 2 machine cycles, 70 states if the condition is not true, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. Now likewise we have G and Z in contrary to ZZ. So JNZ instruction. So JNZ instruction transfers the program execution to the address specified if the 0 flag is 0, right? Okay. If 0 flag is equals to 0 or Z is equals to 0. If 0 flag is equals to 1, then no transfer takes place. So jump on no 0, program execution is transferred to the address location specified if not 0, so or 0 flag is equals to 0. If 0 flag is equals to 1, then no transfer takes place. Now bytes, machine cycle and T states. So bytes, it requires 3 bytes, 2 machine cycles and 7 T states if the condition is false, and it requires 3 bytes, 3 machine cycles and 10 T states if the condition is true. And the associated hex code is C2. Flags, none of the flags are affected. Now let's move on to another set of instructions that is called as LDA. Now LDA instruction which is capable of, so LDA instruction on execution, it's capable of moving the content of the address location specified to the accumulator, right? Again, I'll repeat it. On execution, LDA instruction is capable of moving the content of the memory location specified to the accumulator. That means it loads the accumulator with the content of the 16-bit address. Again, I'll repeat it. LDA instruction loads the accumulator with the content of the 16-bit address. Now, bytes machine cycle in T states. It requires 3 bytes, 4 machine cycles, and 13 T states. Hex code is 3A, and flags, none of the flags are affected. Now, LDAX register pair. Now, in contrast to LDA, where you specify the address, in case of LDAX, address is specified in the register pair. So LDAX on execution, the content of the memory location pointed to by the register pair is loaded onto the accumulator. Again, I'll repeat it. The content of the memory location pointed to by the register pair is loaded onto the accumulator. So that is the way how LDAX instruction works. In case of LDA, it is this specified address in the instruction itself. In case of LDAX, the address is specified in the register pair. Now it requires 1 machine cycle, it requires 1 byte, 2 machine cycles, and 7 T states. Again, I'll repeat it. It requires 1 byte, 2 machine cycles, and 7 T states. Now the associated hex codes along with the register pairs are specified for your perusal, and flags, none of the flags are affected. Now LHLD. Now LHLD instruction on execution, the content of the memory location specified is loaded onto the register L, and the content of the next memory location is loaded onto H. Again, I'll repeat it. On execution, LHLD moves the content of the address location specified to the register L and then increments the register, and the content of the next memory location is loaded onto register H. So here what you need to remember is, we need to remember that the content of higher order address goes to higher order register H, and the content of lower order address goes to lower order register L. Right? So higher order address to higher order register, lower order address to lower order register. Now here it requires 3 bytes, 5 machine cycles, and 16 T states. Again, I'll repeat it. It requires 3 bytes, 5 machine cycles, and 16 T states. And the hex code, associated hex code is 2A, and flags, none of the flags are affected. Now LXI register pair, 16-bit data, right? Okay. So what does this particular instruction do is that LXI on execution, the 16-bit data is loaded onto the register pair. Okay. So 16-bit immediate data is loaded onto the register pair. So this is very much important for you to understand. So whenever LXI instruction is executed, 16-bit immediate data is loaded onto the register pair. Now it requires 3 bytes, 3 machine cycles, and 10 T states. Now the associated hex codes with the register pairs are given for your perusal, so you can go through it. Now flags, none of the flags are affected. Now one of the most important instruction that you have is called as move. Now move instruction, whenever it executes, the content of the source register is moved on to the destination register. Again, I'll re-specify it, re-describe it. The content of the source register is copied onto the destination register, because here I've used two different terms, move and copy. It basically resembles the same operation. So here move basically represents copy, right? So the content of the source register is copied onto the destination register. It requires 1 byte, 1 machine cycle, and 4 T states. Again, I repeat it. It requires 1 byte, 1 machine cycle, and 4 T states. Now, the possible combination of source and destination registers are given. The source registers can be A, B, C, D, E, H, and L. Likewise, destination registers can be A, B, C, D, E, H, and L. Right? So, flags, none of the flags are affected. Now, next instruction that we're going to study is MOV M, RS. So whenever MOV M, RS instruction is executed, it moves the content of the source register and copies it into the address location specified by HL pair. Excuse me. Again, I'll repeat it. On execution, move M, RS instruction moves the content of the source register to the content of the address location held by HL pair. So here the source register is copied to the content of the address location held by HL pair. Now it requires 1 byte, 2 machine cycles, and 70 states. Again, I'll repeat it. It requires 1 byte, 2 machine cycles, and 70 states. Now, hex codes associated with the possible source register combination is provided for your perusal. Now, flags, none of the flags are affected. Now, move RD, M, right? So, what does it do? This particular instruction moves the content of the memory location pointed to by HL pair to the destination register. So what does it do? The content of the memory location pointed to by HL pair are transferred to the destination register. Now bytes, machine cycle, and T states requirement. It requires 1 byte, 2 machine cycles, and 7 T states. Now the associated hex codes with the destination registers given for your perusal. Now no flags are affected. Now likewise, we have the next instruction that is called as MVIR comma data. Now what does this particular instruction do is the 8-bit immediate data is moved onto the register or copied onto the register. Immediate basically means the data that is placed immediately after the opcode for MVIR. So this on execution MVIR comma 8-bit data, it moves the 8-bit immediate data into the register. Now bytes, machine cycle, and T states requirement. So it requires 2 bytes, 2 machine cycles, and 7 T states. Again, I'll repeat it. It requires 2 bytes, 2 machine cycles, and 7 T states. Now the possible combination of MVI instruction with MVI instruction with the registers are given for your perusal with the associated hex codes. Now flag registers, so none of the flags are affected. Now MVI M comma data, 8-bit data. So what does this particular instruction do is the 8-bit immediate data is moved into the memory location pointed to by the HL pair. So here 8-bit immediate data is moved onto the register, moved onto the address location pointed to by the HL pair. Now bytes, machine cycle, and T states requirement. It requires 2 bytes, 3 machine cycles, and 10 T states. Again, I'll repeat it. It requires 2 bytes, 3 machine cycles, and 10 T states. Now hex code associated is 36, and flags, none of the flags are affected. Now next instruction that we have, and it's one of the most important instructions in 8085, that is called as NOP. Now NOP instruction basically stands for no operation. So whenever this instruction is executed, the instruction is fetched, decoded, but no operation is being performed. Now you must be wondering that what may be the utility of NOP instruction. NOP instruction is basically used for creating delay between a successive execution of instructions. So, for an example, if you are supposed to create a clock, right? Okay. So what we can do is between successive execution, what we can do is we can insert NOP instruction. Now it requires 1 byte, 1 machine cycle, and 4 T states. So it will create a delay of 4 T states. Now hex code is 00. Flags, none of the flags are affected. Now ORA R instruction. Now ORA R instruction is capable of performing logical OR between the content of the register and the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. ORAR instruction is capable of performing logical OR between the content of the register and the content of the accumulator, and it's capable of storing the result in the accumulator. It requires 1 byte, 1 machine cycle, and 4 T states, and the associated hex codes with the register combinations are given for your perusal. Zero flag, sign flag, parity flags are affected based on the result of the operation, whereas carry flag and auxiliary carry flag are reset. Now, likewise, we have another instruction that is called as ORAM. Now, what does it do is it basically performs logical OR between the content of the accumulator and the content of the address location pointed to by HL pair. Again, I'll repeat it. It performs logical OR between the content of the accumulator and the content of the address location pointed to by HL pair. Now, it requires 1 byte, 2 machine cycles, and 70 states. Again, I'll repeat it. It requires 1 byte, 2 machine cycles, in 70 states, and the hex code is associated hex code is B6. Now, zero flag, sign flag, and parity flags are affected by the result of the operation, whereas carry flag and auxiliary carry flag are reset. Now ORI data. Now ORI instruction is capable of performing logical OR between the 8-bit data and the content of the accumulator, and the result is stored in the accumulator again, right? Okay. So again, I'll repeat it. ORI is capable of performing logical OR between the 8-bit data and the content of the accumulator, and it's capable of storing the result in the accumulator. Now it requires 2 bytes, 2 machine cycles, and 70 states. Again, I'll repeat it. It requires 2 bytes, 2 machine cycles, and 70 states. Now, hex code is F6. Now, flags, sign flag, zero flag, and sign flag, zero flag, and parity flags are affected by the result of the operation, whereas auxiliary carry and carry flags are reset. Now, out instruction, right? Output address. Now, what out instruction is capable of doing is the content of the accumulators are copied onto the designated output port, right? Again, I'll repeat it. The content of the accumulator is loaded onto the designated output port. In contrary to in, where the content of the input port is loaded onto the accumulator. In case of out, the content of the accumulators are copied onto the designated output port. Now it requires 2 bytes, 3 machine cycles, and 10 T states. Again, I'll repeat it. It requires 2 bytes, 3 machine cycles, and 10 T states. Now hex code, the hex code, associated hex code is D3, and flags, none of the flags are affected. Now PCHL, now this is a very important instruction, right? Now what PCHL instruction does, the content of the register pair H and L are copied to the program counter, right? Again, I'll repeat it. The content of the register pair H and L are copied onto the program counter. H to the higher order bits and L to the lower order bits, right? So here the content of the register pair H and L are moved onto the program counter, where H is moved to the higher order bits and L is moved onto the lower order bits. Now bytes, machine cycle, and T states. So it requires 1 byte, 1 machine cycle, and 6 T states, right? Again, I'll repeat it. It requires 1 byte, 1 machine cycle, and 6 T states. Now hex code is E9. Flags, none of the flags are affected. Now pop register pair RP. Now what pop instruction is capable of doing is the content of the memory location pointed to by the stack pointer are copied to the lower order register of the register pair C, E, L, and flag, and the stack pointer is then incremented, and the content of the memory location memory location pointed to by the stack pointer is copied onto the higher order register of the register pair. So what does it do? It moves the content of the stack pointer to the register pair, the lower order register pair to the lower order address, and the higher order lower order of the stack pointer to the lower order pair, and the higher order of the stack pointer to the higher order of the register pair. So the content of the memory location pointed to by the stack pointer are copied onto the lower order register of the register pair, and the stack pointer is then incremented, and the content of the memory location being pointed to are copied onto the higher order register of the register pair. So associated, so it requires 1 byte, 3 machine cycles, and 10 T states. The associated hex codes are given for your perusal. So none of the flags are affected. Now likewise, in contrary to pop, we have push instruction. The content of the register pairs are copied onto the stack. Right? The content of the register pair are copied onto the stack. The higher order registers B, D, H, and A is pushed onto the stack first, and the content of the lower order register are pushed onto the stack. Right? Okay. So first the higher order registers are pushed onto the stack, then the stack point is decremented, and the content of the lower order registers are pushed onto the stack. Now it requires 1 byte, 3 machine cycles, and 12 T states. The associated hex codes with the register pairs are given for your perusal, and flags, none of the flags are affected. Now let us move on to the next set of instructions that's called as RAL. Now RAL instruction is capable of rotating the content of the accumulator towards the left hand side by 1 position through carry. Okay, so it moves the content of the accumulator by 1 position through the carry flag. Now it requires 1 byte, 1 machine cycle, and 4 T states. Now hex code is 17. Flags. Now carry flag will be modified as per D7, because D7 will be moved on to the carry flag, right? Again, and sign 0 parity and auxiliary carry flags are not affected. Now likewise RAR instruction. Now RAR instruction, the content of the accumulator is rotated right by 1 position. Okay, again I'll repeat it. RAR instruction, the content of the accumulator is rotated right by 1 position through the carry. So here bytes will be, so it requires 1 byte, 1 machine cycle, and 4 T states, and hex code is 1F, and flags, carry flag will be now affected as per D0, right? So it will be modified as per D0. Sign flag, 0 flag, parity, and auxiliary carry flags are not affected. Now, in today's class, we've been through almost 32 instructions of 8085. We've discussed each of the instruction from the perspective of description, byte requirement, machine cycle requirement, T-state requirement, hex code, and flags. So in the next class, we'll continue with the rest of the instructions. So thank you very much.